afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are going to explore circle problems. That's right. Are there any problems better than circle problems? Actually, yes, but today, no. So, let's get to it, shall we, as we listen to Hey Jealousy. We'll listen more towards the end. All right, so got a nice little circle here. The angle in a semicircle is a right angle. This angle, we say it is inscribed in the semicircle. Inscribed because you have all three vertices of the triangle on the circle. And it's inscribed in the semicircle because one of the sides is the diameter of the circle. So what this is saying is no matter where I were to put this point, what I mean by this point is point C. If I put point C over there, let's make it a little bit more different. Let's say it was here. And I drew from A to B, no matter what, that is going to be a right angle, whether it's here, right angle, right there. Any angle inscribed in a semicircle is a right angle. Isn't that awesome? I believe that it is. Okay, so a circle has diameter xy of length 13 centimeters. Let's go ahead and draw that. So we got a circle. That's not a bad freehand circle. We have a diameter here, and we know that the diameter is 13. Z is a point on the circle, so we'll put, I don't know, let's put Z here. Bam. Such that xz, oh, we forgot the diameter is xy, such that xz is 5 centimeters. All right, so we know that this is 5. I'd like to put it out there, but it's kind of in the way. Find the length of yz. So we'll call this x. And hopefully you see what we got here. We have an angle inscribed in a semicircle, so it is a right angle. So we have a right triangle, and so we can use the Pythagorean theorem. I'm not going to call this x because I have an x here. I'm going to call it k, just for kicks. Get it? K for kicks? All right, so now we have k squared plus 5 squared is equal to 13 squared. And actually, I want to write that as 5 squared plus k squared equals 13 squared, because I want you to hopefully see we have another common right triangle, and that is the 5, 12, 13 right triangle. In other words, if I have lengths of 5 and 12, leg lengths of 5 and 12, the hypotenuse is 13. Or if I have a leg of 5 and a hypotenuse of 13, I know the other side is 12. Or if I have a leg of length 12 and a hypotenuse of length 13, I know the other leg is of length 5. These are called common right triangles. Your 3, 4, 5, your 5, 12, 13. Those are the two most prevalent ones. And then there's a 7, 24, 25. There's a couple others, but these three are the most common. So you're going to see this is 12, 25 plus k squared equals 169. K squared equals 144. Take the square root of both sides, and k is equal to 12. Square root of 144 is 12. I really want you to be able to look even at this, not even have to write this, and say, oh, that has to be a 5, 12, 13 triangle, and immediately say k equals 12. All right, next thing, a chord of a circle. The line drawn from the center of a circle at right angles to a chord bisects the chord. First of all, a chord is any line segment that has its endpoints on the circle. So actually, a diameter is a chord. It's just a special chord because it's the diameter. So this is a chord, this is a chord, this is a chord. My pen keeps doing that. This is a chord. So anything like that is a chord. Let me get rid of those. because we're talking about this chord right here. So if I have a chord, which I do right here, and I, excuse me, if I draw a line or a line segment perpendicular to the chord, it bisects the chord. They're equal. And of course, from here to here is equal to from here to here, because they are both radii of the same circle. All right. A circle has a chord of length 10 centimeters. Let's go ahead and draw it. See if I can do. Let's go ahead and draw it. See if I can do. Let's go ahead and draw it. See if I can do as well as I did before. All right, not bad. There's the center. I'll draw the chord right here. And I know that it is of length 10, whatever did it say, centimeters. Okay. So if the radius of the circle is 8 centimeters, find the shortest distance from the center of the circle to the chord. Well, the shortest distance from the center of the circle to the chord is going to be a perpendicular. It's going to be perpendicular. The path is perpendicular to the chord. Surely you can see that is shorter than this, or this, or this. Okay. So that is the closest distance, is going straight there. We always say straight, and what we really mean is perpendicular to this line. Okay. Well, if I draw a perpendicular, it bisects the chord. So this side equals this side, and if the chord is of length 10, then this is of length 5. And they're asking us to find the shortest distance. So that's from here to here. I'll call that D for distance, just to get a little crazy. And if only we knew this length right here, well, holy smokies, we do, because from here to here is a radius of the circle, from the center to the edge of the circle, and these fine folks tell us that that is of length 8. Boys and girls, Pythagorean theorem time. D squared plus 5 squared equals 8 squared. D squared is going to equal, I'm going to skip a step, 64 minus 25. Hope you're okay with that. D squared is equal to 39. So then D is equal to the square root of 39. And that is approximately equal to 6.24. I kind of like square root of 39 unless we're in a real world situation. This really isn't real world, it's just a circle. But if it was in, like how far does a person have to walk, then I like 6.24 better. So this is centimeters, this is centimeters. Okay. The next property and the last property we're going to talk about is the tangent radius property. And all it says is if from a point outside a circle I draw a tangent to the circle, then if I draw a radius from the center to the point of tangency, or the point of contact, then that is perpendicular to the tangent. Okay. What is a tangent? Well, when we say tangent, that is short for tangent line. Okay, and a tangent line touches a curve in exactly one place. Now, I just want to clarify something. We really shouldn't say exactly one place, because we could have a curve like this, and we could have a line like that, where right here, locally, it touches this curve in one place, but it intersects it again later. This is still tangent, because locally, right there, it's only in exactly one spot. So when we say exactly, we really mean locally. So later on, that's going to become important in mathematics. I don't want you to get confused. All right, a tangent of length 10 centimeters is drawn to a circle with radius 7 centimeters. Let's do it. That's a poor circle tough darts. Okay, so I don't know. Let's just say it's from here. And I'll draw the tangent right there. There's my point of tangency, let's say. So I know from here to here is 10. How far is the center of the circle from the end point of the tangent? Well, here's the end point of the tangent. Here's the center of the circle. So if I draw this segment, it's a radius, it is 7, and I know from the theorem it's perpendicular to the tangent line, and so I'm looking for this distance d. Well, kids, right triangle, d squared equals 10 squared plus 7 squared. D squared equals 149. So d is going to be equal to the square root of 149, which cannot be simplified, but if we have a calculator, that's approximately 12.2 centimeters. Again, I would prefer to just leave it as square root of 149. So next, let's tackle this one. Two circles have a common tangent with points of contact at A and B. A common tangent means that the tangent line is tangent to both circles. Yes? So it's common to both of them. It hits these two circles in one point of contact exactly in that local area. The radii are 4 centimeters and 2 centimeters respectively. So ka-ching, ka-ching, 4 and 2, that's obvious. Find the distance between the centers of the circle given that AB is 7 centimeters. All right, so I took the liberty of enlarging this, cutting and pasting, because it'll make it a little easier to explain what's happening. And I already drew in the radii of each circle, so let me just put in the centers there. We'll call this center C. We'll call this center D. And then let me draw a line connecting the centers. So that'd be like that, because that's what we're looking for. And let's go ahead and label whatever we have right now. And what we have is that the radii are 4 centimeters and 2 centimeters respectively, and I know that AB is equal to 7. And I have to find this. This is X. Okay, so what are we going to do here? Because we do know, well, let's go ahead and do this. We do know that these are right angles because they are radii drawn to points of tangency. So we got that going for us, but we don't have any right triangles or anything that's going to help us. But here's what we do have. Since these radii are drawn to points of tangency and the tangent line is a common tangent, then those radii are parallel. They are parallel. So if I were to take a, let's see, if I were to draw a line segment straight over from the center of C until I hit this radii such that it's parallel to AB, I got a couple things going for me. If it's parallel, then I know that this is 2 and this is 2. It's going to bisect this. And I also know that this is of length 7, and I also know that this is a right triangle. So holy smokes, look what we just did there by just drawing an auxiliary line, a line that really wasn't part of the question until we made it, which is totally okay as long as we can justify the length, which we can, and the fact that it's going to be parallel. We drew it that way, and it's perpendicular. So here we go, kids. X squared, not plus, is equal to 2 squared plus 7 squared. So x squared is going to be equal to 53, which means the distance between the centers is about square root of 153, not 153, square root of 53 centimeters. Using our calculator, that is approximately equal to 7.28 centimeters. Okay, I am done with that one. Hope you enjoyed it. I certainly did that. And with that, I am